sure. Let's do that. We'll fix that.
5.
I can fix that.
Yeah.
I have figured somebody would ask me eventually, but we waited till you.
I was gonna ask. I'm gonna do a parachute, or I'm doing a parachute.
Okay.
I spent all day yesterday trying to mesh it on a full-size parachute, and it did not like the mesh.
You know, you really should do that two-dimensionally. You should.
I should.
Because it's axisymmetric. There's no real benefit for it to be three-dimensional. Although it's a little difficult to figure out what the area. That becomes. I don't know how to do that. That's the thing that I was saying.
Mesh it. Well, I was just gonna ask. I'm having problems with the size because it's not.
It was already due at midnight.
What?
Oh, I thought it said.
Yeah, I thought it was. Yeah.
Well, this midnight's the start of the day. I gotta go to the
I
midnight.
can scale it down. Because I should get the same drag code.
This midnight is the start of the day. I submitted. What the fudge? Let's see. I don't have it like so it turns off yet. But so when did I say this did? It's on the assignment sheet that says it's did. Well, just ignore that.
I was looking for.
I can hide this thing. I'm just gonna hit cancel because I don't know what the hell I just did.
All right.
But it said it was due at midnight.
Okay.
So. All right. I'm not sure what you were asking.
Is it okay if I scale it? Because it just ends this being.
Sure.
I get the same drag coefficient, correct? If I scale it.
No.
No. Okay.
I don't think so. Well. Let me think. I think it'd be fine. Why is this scale? Why would the scale matter?
Because ANSYS is with the student license, you're only allowed a certain number of. Like the mesh is too big for the student version.
But so that the mesh should be scaled then. It seems to me that it wouldn't.
Well, it's more the thickness is the issue. So like the parachute, it's like 35 feet in diameter, and then like the thickness of the fabric is 0.05 inches. So the problem is the mesh size is I have to do very small.
Yeah. I don't know, man. I'm thinking that this ambition could make it tough for you. But it's fine with me, and maybe that's the thing that you're trying to look out after.
Okay.
Anyway, so the previous topics from previous exams, because this is a cumulative. Remember, exam 1 was fluid statics and kinematics, so we started out with chapter 1, day 1, basic concepts. And chapter 2 was fluid properties, and chapter 3 was most of the static forces. We spent some days, so we only spent like 1 day on chapter 1, 1 day on chapter 2, and then we spent several on chapter 3, and that was the majority of what exam 1 was about. We did fluid kinematics and visualization, but that was really just sort of a stopgap for things. We didn't really ask much about that. Then exam 2 is really on fluid dynamics, or that's how I would categorize it. And there's a big chunk of Bernoulli, and then momentum, which is really, like you think of thrust. That's how I think of it, as being the reaction forces that you get because of flow. And then Buckingham Pie, and then lift and drag, right? So we covered a lot of stuff on exam 2. And then now the stuff that's on the final exam, but remember that it's a cumulative, but this is stuff we've covered since exam 2. We did chapters 9 and 15, so there's really, there's not going to be any mathematical topics on this, but there could be some general types of questions. Not stuff that, I don't know, that you would necessarily study for, but concepts and that type of thing. And some of those concepts could be related to what's represented here in these Navier-Stokes equations, whereas we're not going to solve anything with the Navier-Stokes equations. We still might want to have a general understanding of what they represent. I don't think I would ask anything about the streamline functions and the velocity potential, but they are things that we should kind of know of their existence. And definitely not anything about the Laplace's equation and potential flow, but these are conditions. We never really covered anything along those lines. But they're on the equation sheet, so I included them here. Flow in pipes is chapter 8, so we've done some pipe with laminar and turbulent transition, just knowing where things are where that the Reynolds number limit is and the Reynolds number we're using. We didn't really do anything with entrance length, but it was on the equation sheet, so I put it on there. Here's where we get the major and minor losses. So there's probably likely going to be a problem about this. Turbo machinery, I didn't assign homework, but I put some homework up there suggesting that you work through some problems related to this. The big equation, I've updated the equation sheet. Now it's up to Rev 4. If you're interested in a copy of it, I printed out several here, so you can. It's really the only thing I changed is I put it's on the one that says the final exam one, so it's like page, I guess, page 5 or the third of the double-sided pages. There you go. And I added the Euler's equation in there because I noticed, hey, it was missing the turbo machinery equation. Hydraulic power in and out, pump efficiency, net positive suction head as a topic to know things about, pump similitude laws or the affinity law. I like the affinity laws, sounds better to me. And pump specific speed. So those are the big topics, and we have a bunch of old problems from Coast Guard Academy. I almost said Merchant Marine Academy. These are from older exams that existed before, and then we also have some problems. I only had 3 problems this time from Munson's review problems. I was thinking about adding some more, but I was like, I think this is enough stuff to get you going. So, do we have any requests, either specific problems or problem types? We can make up some shit, or we can stuff. Or we can.
There was something you mentioned yesterday.
What's the one where it compares like scaled down things and the properties and how they react?
Okay. Well, for pumps they have the similitude stuff, but there's also we might do the the similitude as it relates to Chapter 7 Buckingham Pie.
Yeah.
There's the models and that kind of thing. All right. Well, we could let's see. We do a couple problems then from there. So I have my good friend Sean's outlines. Pick something out of there. So there you go. Dimensional analysis and similitude. Yeah, it's fun to just pick this stuff off of the topic and see if find something that's going to be. This makes for a great video. So I don't have the answers to this.
Oh, can you do the surface, like the truck with the water in the back,
Free surface.
Free surface, yeah, that one.
Oh, you mean the guy like on a truck?
Yeah.
And that kind of thing? Yeah, we could try to do that. I had to pick up another problem though, somewhere. I don't know if I can find a problem. There's not too many of those problems to select from. There's some,
It won't be on the exam.
well, I haven't ripped the exam yet because of procrastination. But I don't know. That's not. I don't think I asked anything from that in the first exam. Right? Well, that would have been on the first exam.
Yeah, I thought there was a truck going up the hill or something.
I think those are homework.
Yeah, the homework one, as I recall, was relatively difficult.
Yeah.
Had a little bit, had just a little twist to it. Wasn't much.
I think the truck going up the hill on an angle.
Yeah, so you had to figure out the angle. I ran across that one and I was like, ooh, I want to make you think a little bit. And then people didn't think a lot of it. Didn't think at all. Yeah, so I'm not finding one of these.
You basically just had to add the angle of the ground to it, correct?
Yeah, you had to go to relative thing. So you had to really the free body diagram was the savior, or I guess free body diagram combined.
The water would have sloshed
inertial
back
body
to
diagram,
flat in the
yeah.
back of the truck, so the truck would have been like this, the water would have been like this.
Yeah, and so you always have to draw the line, the angles like really, really carefully to try to get before we get a problem there. I think we had to stick with the script in terms of these problems.
Okay.
Or let me.
It was on your sheet from yesterday, so.
Was it on my sheet from yesterday? Let me pause here just for a second. We got 10 minutes into this. It's not really any usefulness, but let me pause. It is.
It's on the first two.
Yeah, I'm still looking to try to find a problem that's related to that that can help you or be useful. Oh, I didn't print those out either. Okay, well, here's one last resort we go to our good friend Munson Young. I've never even tried to pronounce the name. They had two I's next to each other. I don't know. Hello. So, fluid statics and let's see, barometric pressure, monometry, there's a rigid body motion. Probably have uses, but okay, here's a problem. All right, so pressure variation in a accelerating tank. So try to move these around. So in this one, for the given cross section here, we've got a little vent going on and some little fluid inside, and the fluid is let's get a little transducer. I don't know what a transducer does yet. Let's see. So that's 0.5 feet above the transducer. We have spot 1 and 2, and this is fuel. Let's see what kind of fuel. So it's the cross section of a fuel tank of an experimental vehicle shown. The rectangular vent. A tank is vented to the atmosphere and specific gravity. There you go. We need the SG of 0.65. Pressure transducer is located in the side as illustrated during the testing of the vehicle. The tank is subjected to an acceleration in the Y direction, which is for some reason going to the right there. And we're going to have a thing that comes to Z. I did a bad job on mine. You'll see soon with what I'm trying to copy this down as we're going through here. That accelerates at AY, and the pressure is in pounds per square foot at the producer. What is the maximum acceleration that can occur for fuel level drops below the transducer? Right, and then this thing is 1.5 feet, I guess, total across. During testing, the tank is subjected to a constant linear acceleration. Determine an expression. Okay, I hate expressions, but it's okay. But that's what we're trying to find, expression for that relates acceleration in the Y direction and pressure. And then B, maximum acceleration, so it won't go below, so not below transducer. All right, so the big idea in this is to try to find some kind of variable relationship that's going to result, based on what we know, into what we want to find. It has a lot of some problems like this, but we haven't covered many of them. So the first part of this isn't really necessarily something that we would generally do, but it's all about the slope, right? That's the thing that we know, is that the slope is going to be related. And the slope here is going to be rise over run, or it's going to be dz over dy. and we're going to say that's going to be related to the slope, which ends up being the ratio of the accelerations. If we go back to what we had here, we can see that we have the dz dy is equal to the negative ay g g plus az, right? So it's the ratio of these accelerations. We could go back to try to prove that, but we can also have it on the equation so we can just write it down. There's not going to be any acceleration in the z direction. We're assuming this thing is only accelerating in the y direction.
Is that pressure? What is the AY and what?
AY and G.
No, for question A.
Expression that relates AY and pressure. Oh yeah, it says the word pressure. Oh yeah. Sometimes I just give up on a word like near the end of it. Just like, yeah, I know what I meant. Thoughts just trail off right there. I put a dot right after it. So to start with, we could actually we could find how things are related in the z direction. Right, so we could write that this is the same in terms of a scaling of the thing, that we could also say that z is related to the width of the thing. Right? So we have the width, which is the y. So we'll take point. I guess we decided to go from the center out, right? So, yeah. So to measure what that slope is going to be from here to there. So we're going to take that in terms of the depth and go 0.75 onto the thing as a ratio, and set that equal to, of course, well, we don't know the acceleration in y, but we do know the acceleration of gravity. I guess we left it as g. It's supposed to be y. So we can find z as a function of, so 0.75, and then well, we could also, and this is a negative slope, right? So what we're looking here in the canister is also a negative, so that'll get rid of those negatives. That's nice. So we go ay divided by g. And then we can also say that, well, one thing we know about pressure is that it's going to be related, and maybe I want to make a bigger tank to try to draw these out here, because it's not, I made my tank a little small. Lines of constant pressure are, in this case, are going to be parallel to each other, like this right there. So they're really going to vary down that way, perpendicular to each other. Yeah, we didn't really do this before. That's because there's no acceleration in the vertical direction. So we could say that in a general, we could actually think of this as being the height right here, even though we would normally think of it the height this way, but this is the virtual height, you would say, right here. So we could say that this relationship is still going to hold, and now we can substitute, not here, I'm sorry, there, the h. Recall that this is, from the problem that we had a specific gravity of 0.65. So we could have that the pressure is going to be equal to, I'm going to put the 0.65 in front here, 0.65, and we're in feet units, so we'll go 62.4 for the gamma. So this is going to be, this right here represents the gamma of this fuel. And and then we're looking for an expression for above the transducer. This is like a terrible problem, that's all right. It's not like a representative problem, because we just haven't done this. We could say that we have 0.5 minus this right here, so that's gonna be the 0.5, and then minus the rest of this h, which is 0.75. Sorry. AY divided by 32.2. So if we had a expression for the pressure that depended on its location, it was like 20.3 minus, and this ends up being, oops, I guess I kept this as a G, sorry. That should have been a G. Is that right? Yeah, okay, kept it as a G. I don't know why we didn't put a number in there. Personally, 30.4, and then AY divided by G. So that's supposed to be the expression. And so this would be when trying to find what the pressure distribution was based on the acceleration. Right, so this is this is the pressure at the transducer. This is an expression that relates this pressure and the pressure of the transducer. So we're trying to see, because that's what that variable is up above. I'm sorry, once again, I moved the thing below too far. So when the thing actually hits that location right there, right? And so this first problem right here, this first A, isn't something that we've done before, so it's not something I would ask. But maybe this one right here is a fairly straightforward thing, where it's at the maximum acceleration, so it wouldn't go below the transducer. So you have to kind of think about okay, so the Z is, we're going to set that Z equal to 0.5. So that becomes a fairly straightforward type of thing. We still have that negative and that negative, so that slope does obey each other. I mean, this whole negative that we started with up here, it is in essence just, just the reality of the thing. Yeah, it's going to be a negative slope.
So is it literally just plugging the Z in?
Yeah, it really is. Yes.
Oh, okay.
Yeah. So it simply comes like 0.5 divided by 0.75 is going to be equal to
32.2.
Yeah, just AY divided by 32.2. So I think this will come out to the right thing. So, yeah. We just go 32.2, 0.5 times 0.75 divided. So it should come out to be like, AY should be like 21.47 feet per second squared. So they become simple problems. I overcomplicated it by looking at their overcomplication of the thing. Honestly, I don't value these problems all that much in terms of like the big picture complication thing, or a scenario that comes up sufficiently that it would justify dedicating that much to the exam. Do you have other types of problems? We had named another one, right? You said
Buckingham Pie.
Oh yeah, okay. So a Buckingham Pie one, a Buckingham Pie all the way through, or a Buckingham Pie similitude.
Similitude, like
yeah,
you have a scale model of something, it's a little bit different.
Gotcha. Okay, let me try to find one quickly here that's along those lines, if I can. Alright, so I'm not sure what we did in the last, in the previous review session, if we covered some of these, but these were the problems that we had available to us, where we had a thin rectangular plate is towed through seawater at an average velocity at 5 miles per hour. The plate is held in a vertical position and protects, and this feels like we did this one in the previous one. We could do it again. Show me the fruit number similarity. Yeah. This is probably one. Yeah, so this thin plate is towed behind through seawater at an average velocity at 5 miles per hour. The plate is held in a vertical position and projects above the undisturbed level of the water to a height z. Right, so we're kind of like looking at a plate that's like this right here. Here's the water that's around the thing, and someone is like dragging it along. And the scale, let's see, I guess, well, okay, so they're going 5 miles per hour in the real thing in seawater. And the scale is 1/4 of the model. It's used to predict the drag on the plate. And the model of fluid is also seawater. So both of them are seawater. So that actually makes it kind of easier because you don't have to do similarity between fluid properties. But assuming that fluid number similarity must be maintained, determine the required model velocity. So
2.5 miles an hour.
5 miles an hour.
2.5 miles.
So assuming that, determine the required velocity. So we go to Froude number, which we might not remember off the top of our heads, but it's yeah. So Froude is V over the square root of GL, where L is a characteristic length of the thing. So when we say it's got to be similar, that we need to make these similar to each other. So maybe I'll not label the other one, and we don't have to. You know, the G is always going to be the same, so relatively easy there. So in another way to write this out, or the way that I would prefer to write it out often, is to go V, and so that's just well, I want to actually do the other way around. This is asking for the model, right? So I'll do it this way here. Vm is going to be equal to, and you go square root of G divided by the square root of Gm. You can think of that as its own ratio. And then the square root of L over the square root of, oh, no, wait, I'm going to say, oh, yeah, this is going to be the Lm, and then times V. So I like to organize them that way, and then you can think of each of these as a scaling thing. But of course, this one's going to go to 1 because we're not going to change what the gravity is. And this one's going to be the square root of the real thing divided by the model. So we know that that's going to be the square root let's see, I'm going to do this wrong on it. I got it wrong.
Vm over the
You're
square
right.
root of Gm.
You're right.
Equals V over square root of GL.
Is this one wrong?
I have V's on the top of both of them. And then
Yeah, I think this would be M's. Yeah, right up there. Yeah.
that's the
Yeah, because that was going to multiply and that one's going to multiply and these still remain on the bottom. Yeah, okay. But anyway, so this is going to be 1 over 4.
square root of 1 over 4. This is the 4, right? This one's the 4 times the size of that one, so it has to be on the bottom. And then this one is going to be times 5. And that would end up giving us 2.5 miles per hour. Not an exciting problem. What is the required value of Zm over Z? Where Z is this length right here. And where this is the length, right?
Just a quarter, isn't it?
It's gonna be 0.25 because it's the same. Because your knowledge of Buckingham Pie here is really being tested. Is that you would, if you're going to do a Buckingham Pie on this, you don't have to do anything. You just recognize that when doing a scale, the scales are just going to, the scale of the length is going to be the same as the scale of the Z. So when Z over Z, Zm over Z is the same thing as Lm over L, which is the same thing as 1 over 4, right? So the answer to this is just going to be quarter in. 1/4. And then last is a measured drag of 1 pound on the model will correspond to what drag on the prototype? And the hint was that this ends up the dimensionless drag coefficient right here is like that right there, right where we have so. We could even just write it out on here. So just go 1 divided by, well, let me write out the equation. I'm sorry. I was lazy. I'm like drag divided by rho v squared L squared, right? Is going to be equal to the model rho m v squared m L squared m. So when doing this right here, right? Let's see, measure 1 drag on the model, right? So we're gonna find this guy, divide him. These are going to cancel out, so I'm gonna get rid of that. The v squared and we don't have to do anything about units because of the they would all cancel. All of them will cancel out. So this is going to be 5 squared. This would be 4 squared. It's going to be equal to the drag of the model, which is 1, divided by Vm squared, which we said was 2.5 squared. And then this would be 1 squared. So we end up finding we're going to predict that the drag of the real thing is going to be 64 pounds.
You did this one in your last review session.
Did I? Sorry about that. I only have so many that are like prepared ahead of time, and trying to think on my feet is not a fun thing to try to attempt to do, although we could try to find another one here somewhere.
So my biggest thing is, my question is going from like actually doing the Buckingham Pie out to then using it to solve the problem.
Yeah,
So you get an equation out of the Buckingham Pie and then use that?
I like to do that,
Okay.
but that's a long problem
Yeah.
to be asking on an exam.
Okay.
But then again, it is a final exam, right? So let me think. I mean, we have some of these right here where we have determination of pi terms.
What's 7.7 R? Because that actually has an answer to it.
The water velocity at a certain point of the scale, right? So they still have.
I just wanted the previous probably just did.
Yeah, but this one right here is a little bit like or this next one right here, because, let me see, 7.9R.
If I remember right, the Buckingham Pie homework that we did, only one of like the 3 problems that we did on that, you actually had to find an answer with the thing.
Yeah, and in both of these problems, I made these as, I would usually give you the pi terms in this one right here.
Okay.
But, you might be able to find what these pi terms are, so we can work through this as if it's a Buckingham Pie, to get these terms, right in there. But you know, one of the things we'll notice is that this scale is obvious, so we don't have to do, and this one, of course, we could predict. This is one that we don't necessarily know, right? That's one, that we need to know ahead of time, and to know what we would use as our repeating variables would be something that we would want to put in here. You know, the pressure drop per unit length, and we have the diameter. They told us that it has using rubber at the same time as the pressure drop in gasoline. There's one more. There's what is the pressure value onto the thing? Yeah. Should probably do a refresher on a Buckingham Pie. So maybe we should try this as a Buckingham Pie problem, as a refresher. So we have delta PL. All right, is going to be one of our variables, and that delta PL. Let's see, that's going to be a force per length squared per length, right? So I think it's going to be FL cubed. I think so. I don't think we will have that. So we know that pressure is, let me write it out the way that we normally do. We usually do them next to each other, not underneath. We go F, L, and I think we go -3 onto that. Other variables we're going to have the diameter, right, which is a length. We can leave off the roughness in there. We know that's going to be true. So we have the velocity. It's definitely going to be related to the thing. So that's going to be LT -1. We're going to have the density. But remember that we probably want to use F because we already started with an F right there. So we use FLT. So density, that's not one that we normally would be able to recall. That's going to be FL -4 T2. So FL -4 T2. And then, of course, this is what is the water? So I think we just implied that we're going to have the viscosity. We already know the answer here, so we're just trying to work through the problem. But see, viscosity once again, and this dynamic viscosity is FL -2 T. So our step 1 is we're going to list all the variables and count them up. So step 1, list all the variables. Delta P L D V rho mu. So that's 1, 2, 3, 4, 5. So if K equals 5. Next step is to find the F and the L and the T and count those. We use all 3 of them, F, L, and T. So R is equal to 3. I guess that was right here. R is equal to 3. We need step 2. Step 3 is to find k minus r, or 5 minus 3 is 2, and that's the number of pi terms. 4, we would pick the repeating variables. Generally speaking, we're going to give them to you, and there should be oh yeah, there should be 3 repeating variables. There's always, it's going to be equal to number r, so there should be 3 repeating variables. And those repeating variables, you can usually kind of guess what they're going to be. It's definitely going to be v, velocity. So there's a couple of rules. We didn't really cover some of these rules, but you can kind of like think about them. Through is that you want to make sure you cover the F, L, and T all need to be represented, and we want to try to probably do them in the simplest amount. So velocity is a good one because it has time. Diameter is a good one because it's simple, only L. So then we haven't represented F. So we really, we have a choice between either density, where we represent F, or viscosity. So you can do either one to represent it, but I think density is going to be a better one. I can kind of forecast it. If you did viscosity, I think it would get kind of screwy up here. But so you can put those in there because we know that we already kind of predict ahead of time that Reynolds number is going to fall out from here. So we don't necessarily have to do Reynolds number because we know that it's going to happen. But if we were to do this, well, so the first one we pick when we go to 5 is we pick the main guy to do, like find, do this for the first pi, right? So let's see if I can remember off the top of my head how to set one of these things up. So we're going to do this for the delta PL. We go delta PL, and we're going to go, is going to be equal to V to the A times D to the B times rho to the C, right? And see if hopefully I made these things wide enough. I didn't quite make them wide enough. So yeah, right here, we're going with F, L minus 3 underneath this. The V, so parentheses, and go L, T minus 1 raised to the A. We go L raised to the B, and then the last one, maybe I'll give myself some more room there. That was a terrible row. F, L minus 4 T2 raised to the C. And then I go F, L, and T. And this should be equal to, yeah, that doesn't matter. So for the F, it's going to be 1. This is going to be 0, 0, and this guy will be C. And that should be equal to 0. So if I were to write that equation below, I immediately go C is equal to negative 1. Because 1 plus C is equal to 0, so C equals to negative 1. Then here I'm going to go negative 3. And then it's going to be A, B, and then negative 4C. All right. right, so let's see, I'll write down -3 plus A plus B minus 4C is equal to 0, and therefore -3 plus A plus B, and then minus, so the action would be +4 is equal. So what we've decided there is that A plus B is equal to -1, right? Because that would have been +1 here, but we'll bring them over to the other side, so. Then, lastly, up here, we're just gonna say that we have 0, -A, 0, and then, 2C. Is that right? Is equal to 0. So our last statement is that -A plus 2C is equal to 0. And so therefore, we would say that A is equal to -2, right? Because that would be -A minus 2 is equal to 0, so this must be equal to -2. So if we did this thing correctly, take a peek back what we did before. Oh, and then by the way, B should be equal to, B should be equal to 1, right? The -2 plus B, yeah, so B is equal to 1. So if we plug them back into there, we could say that del P L equal to VA, so V to the -2, D to the 1, and then rho is to the -1. So collecting them together, pi 1 is going to be delta P. Oh, wait a minute, I think I'm not supposed to say equal. Am I supposed to say equal? No, I'm
Wait, why is it rho?
excuse me?
Where's the rho? No, on pi 2.
This one?
Oh, never mind, okay. You changed it from G to rho, and then.
I think it actually, it just looked like a G. I said at one point, that's a terrible, that was a terrible rho.
Sorry, I had a G and I was very confused.
Yeah, no, I got you. I think I'm messing something up here when I go to the, I don't think it's supposed to be equals right there, right? I'm supposed to multiply all those things, but that times that times that times that. Right, so, didn't meant to go equals. Because it's supposed to be times D divided by V squared and rho. And that's what we predicted that we were going to get up here. And then honestly, because we see the combination, you know, so we had these 3 repeating terms. One of the other non-repeating terms, that's what we do for 6, is the other non-repeating terms. The other non-repeating term is going to be mu, and we know just from, you know, our experience that Reynolds number is going to fall out there. So if we were to put all of these things together, we would have, what we would have is pi 2 would be mu divided by V, D, and rho, which is just Reynolds number upside down. So we would say, you know, just go ahead and flip the thing around and say that we have that right there. So when we get to the problem, the similarity problem right here, we know that this is a dependent pi term. We also have the roughness shown in here. So here is the thing that we're trying to do, and then we go into attempt to use it, which is really the whole point of the Buckingham Pie. is to try to use it. So reading the rest of the question, the pressure drop per unit length is 0.25 inches diameter. A gasoline fuel line is to be determined from a laboratory test using the same tubing, but with water instead of fuel. The pressure drop at a gasoline velocity of 1 foot per second is of interest. It's in what water velocity is required. Well, you have to make a decision. Should we first take care of this part right here to try to get similarity? Because that's our main similarity law, or our modeling law, is that you want to get the similitude rules, is you want to get all of the pi terms. The modeling law is to get the dependent pi terms to equal each other before you could do the main pi term, right? Because what we've really written out, I never did finish out the thing to do there. We should, by the way, 7, we should have checked out the, make sure that this expression right here is, right there is dimensionless. And then 8 is to write out the main part right there. So let's just go ahead and assume that I did the dimensionless check onto there. But the big idea is to say that dp, that's supposed to be an L right there. D divided by V squared over rho is a function of VD rho over mu, right there, right? So that's like the big idea of the Buckingham Pie, that we have that this is a dependent pi term and this is the main pi term. So then we can follow the law right in there. So we have to say that rho VD over mu is going to be equal to rho m Vm dm over mu m. They say in the problem that they're going to use the same diameter from the same diameter tubing, so we can get rid of this guy and this guy. As part of that, and now, but they're going to use water instead of gasoline. So we have to look up our values for water and gasoline. And these are in US units, so we should go with those right there. So for British gravitational, we probably have water already memorized. Here's our density of the water, but the viscosity we probably need to look up. And we're also going to have gasoline, which is going to be 1.32, and then a viscosity here. So, and so this is the real one, and this is the model, and so we have the density of gasoline right here of 1.32, and the velocity that we want is the 1 foot per second, and divide by the viscosity here, 6.5, e to the minus 6, and then they're using water here for the model, 1.94. We want to find the velocity in the model. We take the viscosity of the model, 2.34 e minus 5. So the velocity of the model, so 1.32, 1.94 divided 6.5, 2.34. So you get 2.450 feet per second. That's what we're going to predict in here. Yep. I got 2.47. I guess maybe I used something different. How come I have this? Oh, I see. I did. Oh, I just made it slightly different. I used, because I was already using, I went to use the Reynolds number that's just ever so slightly easier, where I combine the density and dynamic viscosity together for the kinematic viscosity. And then, so the next part of the question asks, at the properly scaled velocity for part A, the pressure drop per unit length was found to be 0.45 pounds per square foot per foot. What is the predicted pressure drop per unit length for the gasoline line? So we want to use what we got out of the Buckingham Pie. And take that delta P L D V squared rho equals delta P L model, the diameter of the model, the velocity squared of the model, and the density of the model. But we recall that we're using the same tubing, so the diameters cancel out. And this is the thing we want to find, right? And this is the one that we just found from our experiment. And we'll just go ahead and use the same units in there. So delta P L divided by V squared, which is that's one, right? 1 foot per square, one foot per second. The density,
If you use the velocity we found, for the model, that's the model.
yeah, the velocity is the one we just found for the model. That's no problem. And the density is going to be for the gasoline, 1.32, because this is the real thing. It's going to be equal to, we just found from the experiment this was 0.45. That needs to be squared. Sorry, velocity squared. Forgot that. Here you go, 2.45 squared, and here's the 1.94, and it's for the model right there. So our conclusion I should have just used, it's already in my calculator, so I should just 0.94 divided 1.32. So we end up with 0.05101, and these are pounds per square foot per foot. Which I believe is what they, what the answer is. So, once again, this is a half-hour problem on exam, easily. I think on my rough draft exam 2, when I did the Buckingham Pie, it took me 11 minutes to do, 11 and a half minutes to do the Buckingham Pie problem, and I decided that that was too long, so I cut that one out to bring the exam time down. My original exam time was 40.5 minutes, and I'm like, that's too long. It's close though, because I usually go aim for the 37.5, right, for double time, and so I brought it down to 29 minutes for me, which was, still people had, some people had, a difficult time finishing it. I can't stand that aspect of exams, but I don't know any way around it, the fact that they're timed.
It's like, in Massachusetts, they do MCAS, which is the standardized testing, and you get unlimited time, you get the whole school day to do it. Versus like the SAT, and it's just like, I did so much better on the unlimited time exams than I did. It's like the same types of questions, but like, I got a perfect score on MCAS and the SAT, just to the aspect of it being timed.
The timing aspect of it is
It's not the fact that I don't have enough
unfortunate,
time.
but I mean, here in college, I mean, you just don't have that time, amount of time to like dedicate to things. But maybe if you want to extend college by several weeks, right? You want to make it every semester a couple weeks longer. So there are some places that have exam periods, right? And professors put in for this exam period, right? So they can go ahead and test you someplace else. Right? Everybody gets done one. Let's look for other problem types. Right here we go to a piping one. I have, I don't know if you had a chance to look over the different types of problems. I did put together this, once again, I only have so much time, so I picked as many as I could without giving you everything. Had to hold something back, right? So give myself a little bit of resources to draw from. But this was an amalgamation of various problems that were applicable. And so some of them on the first first pages are just short answer problems, right? They're things that might take just a couple seconds or a couple minutes to do. Hopefully, I was thinking of actually making a multiple choice section, but I don't know if I have the bravery. Writing multiple, I dislike taking multiple choice questions almost as much as I dislike writing multiple choice questions.
Writing is way worse than taking.
Well, you just, there's so many pitfalls, right? The language is difficult, right? You try to imply, you don't realize how someone could misread something, right? Because I know what I mean, but I don't know how I can, I have to be really careful to try to think about all the different ways someone could read the problem and make it ambiguous where I had no idea that it could be misread in this manner. It's quite a conundrum right in there. But here's a pump modeling one right in there. To show you where it's a net positive suction head problem.
Can you do something with cavitation?
Do something what?
With cavitation.
Well, this really is a cavitation problem right here, where we go to where we want to write out the net positive suction head relationship, which is given on the equation sheet. By the way, there's some equation sheets right there if you don't have one. And there's a slight change, but not much onto this one. We have the equation here for the net positive suction head available, which is the atmospheric divided by gamma minus the lift minus the pressure drop in the inlet minus the vapor pressure divided by gamma, right? So everything in the head version of the thing. So net positive suction head available is equal to the atmospheric pressure divided by gamma minus the lift on the inlet, right? So sometimes we call that Z1, right? So we have that lift, how high everything has to be lifted, minus the head losses on the inlet, and then minus the vapor pressure. So, and then we have to find, okay, so we have the gallons per minute. Do they tell us the velocity of the thing? So I don't know if we need the velocity. I feel like we would need it. Only for the head loss, right? So they said that they're going to, okay, so the net positive suction head, a pulmonary peristalsis is the required, right? So from what we have here, the net positive suction head required is equal to 15 feet. So the available one is we're going to take 14.7 times 144 divided by the density of this fluid, or not the density, but the specific weight, divided by 62. minus, it's gonna lift it up. The inlet is 15 feet above the free surface. And the losses are gonna be 2.3, and the vapor pressure is 0.9493. That also needs to be multiplied by 144 to get pounds per square foot, and then also needs to be divided by our 62 by the specific weight. So our 14.7, 144, 62 divided. Right. So, one of the first things that I'd like to do when writing out a problem, at least for me, is to actually do the in-between numbers. So I can see that this is the amount of head that before the other aspects would be available to us to write there, right? And we could actually, as I'm writing, I'll write these out right here.
Is it 34 or 39?
There's a 34, ugly 34. And so these two are like practical concerns, but I kind of almost want to start off by taking that and subtracting from that right there, because it tells me just a little bit more. We're trying to figure, we're really thinking about the margin. Right, so we have 2.205, right? So using that number and that number first together kind of gives us what the practical idea of what net positive suction head available is, right? Because this is when cavitation occurs, and here's what atmospheric is. So we want to kind of, we can make those two comparisons. So subtracting out. So we have like really 31.9 to play with, and we can see that 15 is what we have to here, so we hopefully it won't drop below that. So if I subtract out 15 and I subtract out 2.3, I'm left with 14.64 feet. And because available is less than required, I'm going to predict cavitation. So he said, is cavitation going to be an issue? And you would say yes, because net positive suction head available is less than net positive suction head required. Was it clear why that's an issue in this situation? Okay, right, cool. It's really because of that guy right there.
I think my biggest thing was just like, in terms of, are you always just gonna be given the cavitation pressure?
Yes, otherwise you'd need to have the book with you.
Oh, okay.
Yeah.
Okay.
The vapor pressure.
Yeah.
Yeah.
Okay, I think that was my biggest thing, like,
So if it would ever drop down to this pressure, it would definitely cavitate, but then the pump manufacturer is also telling you, hey, you need at least this much to avoid cavitation, just because of the geometry of but they probably also from tests. They ran the tests and they could say, okay, at these different flow rates, here's where cavitation started. And it's pretty obvious where cavitation starts.
So where does cavitation occur in a venturi? That's like at the nozzle.
It would be right at the nozzle, yeah, right at the constriction, at the smallest spot.
Where it gets bigger, the pressure decreases? Is that what causes the cavitation?
No, it's the velocity causes the cavitation.
Okay.
It's best to think of it in terms of Bernoulli.
Okay.
Is that the total? We have the total pressure is going to remain the same, but there's a play between the static pressure and the dynamic pressure.
Okay.
So when the dynamic pressure goes high, the static pressure goes low. But it's the static pressure is the one that causes cavitation, right? If that static pressure drops low enough, that's what the fluid, its properties are based on. So it goes below and then starts to we could think of it as boil. Some of these I put them in there before I just, I didn't really do the parallel stuff right here, but that is a short answer type of problem. But I'm not, probably won't ask any parallel problems, but that was like a homework problem that I decided to turn into an extra credit. I still haven't graded that one too, anyway, but I'll see if anybody has done it. Hopefully I'll do that today. It's pretty important to do it. Here's a general piping problem. Piping is probably more important to me than it is to probably other professors. I do a lot of stuff in my professional life with piping. Trying to project my priorities onto you, but let's see. This is usually pump problems, right? Usually trying to find. So the system shown as the following parameters. We want to define the hydraulic pump power that's required for this operation. So this is when doing one of these problems, it's very much the big Bernoulli one right here. This is that equation right there. And then, of course, we will use this power right there.
So it was a tube, I'd squeeze it.
So let's see. I decided to call that 2 and that 1.
Yeah.
So the P2 divided by gamma plus V2 squared divided by 2G plus Z2 going to be equal to P1 over gamma plus V1 squared over 2G plus Z1. And we're going to plus the pump minus the head loss. All right, so, and the head loss is going to be broken down into 2 parts, right? Where head loss is the major and the minor. And the major is F L over D, V squared over 2G. And the minor is KL, V squared over 2G. So if we don't see, so let me write that down. FL is going to be F times L over D, V squared over 2G, plus the total KL, V squared over 2G. So if we don't know the velocity, that's probably the first thing that we should try to find. And that's going to require, I guess I wrote it as Q in here, so I'll keep it as Q. I tried to make that transition this semester. There's too many places that write it. I don't think they need to area any other place, so I don't need to calculate it out specifically. It was given to, the flow was given to us both in gallons per minute and cubic feet per second. So we'll do everything in feet. 4.737 divided by pi over 4, and the diameter is 6 inches, so it's 0.5 feet. So 4.737 pi 4. So I think we end up with 24.13 feet per second. They being me in the past, didn't give us F in here, this friction factor. So we're going to need to find that. And in order to find that, we need 2 things. We're going to go to the Moody diagram. Before we go to the Moody diagram, we need to know the friction, we need to know the roughness ratio and the Reynolds number. So the Reynolds number is going to be V, did they already do this for us? Yeah, they did, okay. I did these in a weird order right there. I guess not weird. 24.13. The density is 1.94, given to us there. The diameter is 0.5, and the viscosity was given right here, so we have to look it up, 2.34 E minus 5. Times that, 0.5 times that, 2.34 E minus 5, we get 1 million. So they try to make that a little easier, I guess. The roughness divided by the diameter, the roughness was given as 0.0005, the diameter is 0.5, so I think I could do that in my head, but I don't have that kind of confidence. So 0.0005 divided by 0.5 is 0.001. And now, old man might have to take off his glasses for this. I just haven't never dropped it. Magic ruler here. And go, okay, might as well write on our equation sheet. Why not? There's our 1 million. And then our roughness is 0.001, which should be right here. So we can kind of see where that is right there, right? So there's 0.001, comes over to here. Try to see if I can see that line straight. I think it's 0.0002, right? Very, very close to 0.02. So F 0.02. And then we were given K, right? We were given, we got, let's see. We have a globe valve. We have 2 elbows, 3 elbows, an entrance and an exit. So you can see the sum of the KLs right here. The entrance is going to be 0.5. 3 elbows, and they told us what those are, right? The fittings are threaded. Sorry, they're over here. They're threaded fittings, and they were 90-degree elbow threaded, so they're 1.5 each. So 3 times 1.5. They gave us a globe valve. The globe valve over here was 10. And I don't see anything else except the exit. And they told us the exit was 1. And so I think I get 16 as my total KL. Let me see what I did before in the past. Did I get a total? Didn't even write it down. Nice. So my head losses, and by the way, you could even, take another look up here, and you can see that, well, that right there and that right there are the same, so might as well include them together. And so my F is 0.02. My L over D, and so the total length, they said was 115. divided by the diameter, 0.5, and then add it to the KL. And then I go to V squared, which is 24.13, divided by 2, divided by 32.2. So we have, I'm not gonna do it. No, okay. I was trying to be lazy. So that ends up being 4.6 compared to that 1611. So 24.13 divided 32.2. So you get 186. Damn. Yeah, okay, good. Yeah, I got 186. Good. 0.3, right. I'm looking at my other solution here, and I'm like, shit, that's like that. But I did it separately, that's why. Okay, then I come back up to my Bernoulli up here at the top. Both of these are atmospheric, that's good. These are both gonna be 0. If you take a look here, right? So don't make this mistake where you think this velocity is equal. But even though if it was, they'd both be equal to each other right there. But because they're at the top of a reservoir, the velocities are 0. And they do have 2 different z's going on there, so we'll keep those in there. So plugging back into the equation up above, all right there, I'm going to go 0 plus 0, z2 is 20 feet, right? Equals 0 plus 0 plus z1 is 10 feet. It's really only 10 between the 2. Plus the pump head that's added minus the losses. And so we're going to have the pump head that's being added to the thing. It's funny, I didn't finish the answer to this problem. That's right, we could do the rest of it. And it looks like there's a little bit of a math error right in there too. I don't know. So what we're going to find, we're going to add just 10 to that. It should be 196.3 feet. And then for the pump power, we'll take hydraulic power is going to be equal to gamma HP. I went with the V dot, but Q either way. So this was 62.4. There's 196.3. This was given as 4.737 cubic feet per second, right? So the units work out for this to be in foot-pounds per second, and so we can divide by our 550 to get it into horsepower. And the answer is 105.5 horsepower. And I don't know why, in my solution that I have right here posted, I didn't go. I think maybe the box is like hiding part of the results of the thing. Maybe, I don't know. I'll double check why that doesn't. Must have just made some type of mistake in there. And then the next problem is actually another similar problem. Just so if you want to test yourself, force yourself to go through the. I'm gonna guess this is Dr. Garcia. Darcy is, problem right here, because I can see her solution, I see her here. Right. I should send her an email, say hi. A Christmas card? Anybody send Christmas cards anymore?
Yeah, that's what I'm gonna do.
I sent a Christmas letter, I did for a while, and then like one of my coworkers made fun of us, like, yeah, I'm tired of these Christmas letters, everything's great in our life, this is before Facebook, and when everybody has everything in Facebook, everybody's pretending like they're living this magical life, that everything goes hunky-dory and smooth, right? And, so the next year I sent out this sarcastic one, that was happy, it was a Festivus letter. And I just said, I did all these negative things, and I actually had relatives, because I sent it to all the relatives too. And some of them are like, is he like in some weird religion? Whereas no, it's a TV show. Yeah. But, I put a lot of effort into it, really small effort. I just gave up on it, I was like, whatever. People, angry people, surly people in the world. How are we doing on time?
45 minutes.
What else do you want to do? Let's see, name type of problem. I would also, so these problems are not the only problems that would be asked, right? I would recommend working with your homework, going back over homework and that type of thing as well. I honestly, I just provide the exams because I had some resources available and thought that, hey, this would be a useful thing, right, to try help getting really. I'll try to write an exam where I really, again, so like I kind of measure your ability to solve a fluid mechanics problem. It's not necessarily these problems. But these are a lot of pump ones, weren't they? I didn't realize how many pump ones that I had in there. It's a lot of pump ones. My telegraphing? Do a pump. Learn to do a pump problem. Learn to do a pump problem. Yeah, here's another one. There's no more. There's not more. Oh, flow meter. We didn't do a flow meter problem on exam 2. So there you go. There's some telegraphing going on. Things I want to measure. And then there's stuff from exam 1 that you might like go, oh man, I don't remember even doing that at all. But kind of want you to.
What kind of flow meter though?
Yeah, flow meter. Was that?
So what kind of flow meter though?
Well, here's a nozzle type, right? So, I mean, this is representative problem from, although this is my first year of teaching, I don't know if I wrote this problem. That was day, boy, I had a lot to learn that first year. That was rough. But fall of 2009 is where I made that transition from being an actual engineer to a egghead. No, it's not, all right, it's not very nice. Should try to be a nicer person. But there wasn't that many steps. This was actually a pretty easy problem. Right? It's a nozzle type flow meter. And did I give that in here? I think that's actually on the equation sheet. No, maybe, you know what? I think as part of the problem, no, it is right there. Right? The nozzle type. I tend not to add, is that true? I don't know. The problem is here you need to know the Reynolds number. So I gave the flow right there. Is the flow in the pipe laminar or turbulent? Using the figure below, the value obtained from the figure should be accurate to plus or minus 5%. What is the flow coefficient? Note, use the pipe velocity, not the nozzle velocity. That's an important thing to note right there as part of that. What pressure differential will be displayed on the gauge, right? So, do I have the equations for the flow? Yeah, I got the flow meter right in there. Flow meter equations right here. So, first thing to do is to find what the velocity is going to be in this 1.5 foot pipe. So let's take the area of the pipe. I did find the area of the pipe. Pi over 4, 1.5 squared. I only used 2 sig figs, 3 sig figs back then. That was before my sig fig obsession. .767 square feet. So we want the velocity. We take Q divided by A, and we got 26.5 cubic feet per second. So it's 1.4996. Okay, 1.5. That's enough. Probably what it is. Well, no, maybe I did that, but sorry. Decimal place off. 15. And it's a good idea to get Reynolds number next. Because the first part of this asks, is it laminar or turbulent? So that's going to be what, rho v d over mu. And that was given to us right here. So 1.99. Oh, ballast water, by the way, you know what ballast is? Ballast, okay. The water you keep down in the tanks in the bottom of the ship, so you lower the center of gravity. Velocity, we just found that though. I'm gonna call it 15 because it didn't end that one. And then the diameter is 1.5, and the viscosity is 2.51. E minus 5. So 1.99 times that, 1.5 times it, and then 2.51 E5. We get 1.783 E6. So 1.7 million. So yes, turbulent. Or I guess it wasn't a question. It is turbulent. Turbulent is for the first part right there. And then use the figure below, which is not below. The liar. Liar. I'm sure I'm going to get an email from someone today, tomorrow, tonight, sometime. The figure's not below. Sorry. I lied. All right, so what is that? The 1.7. So I like to, like right when I see this, I know it's somewhere in between, right there. It's probably more over to that side. We also need a beta, by the way, so we might as well calculate that beta. So that's a good idea. And did they give us the dimensions of the nozzle? Seems like it. A 14.4 inch nozzle, right? So the beta is supposed to be little d over big D, or 14.4 inches divided by 18 inches. There must have been a reason for that. 14.4 divided by 18. Oh, 0.8. Look at that. You just knew it. Just had to be, right? And then also, I didn't finish my thought. I like to take the log of that, log base 10. And the log base 10, so that's going to be 10 raised to the 6.25, 6.251. So now when I come over to here, I see that it's going to be 1/4 of the way through, right? Like there's halfway through, and here's one right there, 1/4. So, this is really up here where they're all kind of gathered together. And 8 is the lowest one right here, so somewhere right in there. So you try your best. Sometimes what I will do is I'll I'll mark out this line right there, like, okay, so then it's just like a little bit easier to draw the thing out right in there. So, yeah, 0.992 here, because that's 0.99. And, I don't know. So I'm going to estimate my flow coefficient, which is a CN, 0.992. What did Ted back in the day say? He said 0.99. They're not close enough. And then I take my, we want to do the nozzle. One thing we have to be careful here when we go to this equation right there. That A2, that needs to be the nozzle area as opposed to the pipe area, right? So we already calculated the pipe area, so just try to keep those things, keep them separated. So on my sheet, I have it written down this way right here, so I write the same way. 2 times, now this, we can write this one as delta P. That's what we're really looking for is, we already did the flow coefficient, so this is actually one of the answers to B. C is what is the pressure differential. And I asked for a PSI. Noteworthy that we're going to get pounds per square foot if we keep the base units in here, so just be aware of that. Rho 1 minus beta fourth. So rho 1 minus beta fourth, right there. Should get us what we want, right? So below this, I'll write the thing out. 26.5 is equal to 0.992. We can calculate this to the side or just do it right here. This is the nozzle area, so that's the 14.4 divided by 12. 14.4 divided by 12 squared. And the square root of 2 times the delta P divided by density, which is 1.99, and then 1 minus beta, 0.8, remember that, fourth, there. So there's a little bit of calculator activity going on here. So just try to keep this straight. 26.5 divided by 0.992, and then I'm going to do this one separately. 14.4 divided by 12 squared times pi divided by 4, and then I'm going to divide the other side by that, boom, and then I need to square it, so squared, then I'm going to multiply by 1.99, boom, and now here's the one at 0.8 to the 4 raised, subtract it, change the sign back to that, and that's going to be multiplied, boom, and divided by 2, boom. If I did that correctly, I'm going to get delta P is equal to 327.7, but that's pounds per square foot. I need to divide that by 144 inches squared per foot squared. It's supposed to be squared. And I get 2.276 PSI. How did I do? Yeah, 2.29 is what me in the past said it was going to be, so it's pretty close. And the difficulty in trying to use this as a flow meter is that we needed to know the velocity in order to find the Reynolds number, right? So if you know the pressure, so that's difficulty in asking the question during the exam, is that if I say, hey, here's the flow meter has this pressure, tell me the flow. Well, you kind of need to know what the velocity is in order to find the flow. But to find the velocity, you need to know what the flow is. You have to do like an iteration.
So for those nozzles, flow meters, would that, going back to like earlier, would like, because that would cause cavitation because it's increasing velocity, correct?
Well, I mean, only if it did the velocity too much.
Yeah, but would that screw with the flow meter measurement?
If it did cavitate, yeah, then it would stop it being effective.
Okay.
So you would want to design, one of the, probably one of the bigger issues between whether you use I don't know. You just don't want it to, you don't want it to get close.
Yeah.
But you're usually probably pretty okay
Yeah.
if you're on the discharge side of something, because the pressures are high.
Yeah.
Right? It's really the cavitation thing becomes a real big issue when you're on the suction side of a pump, because you might already be below atmospheric pressure.
Yeah.
Right?
Okay.
And some pumps can't even, this is more information than you want, but a lot of pumps are arranged in such a way that you need to prime them first before they'll actually suck, right? So a centrifugal pump, even without the cavitation issue, does not want to be in this arrangement that they show in that problem that we well, that one's okay. But in the original cavitation problem, centrifugal pumps are not very good at doing that. So one, at least on one of the ships I was on as a cadet, one of my jobs was to pump the bilges, right? We don't pump them overboard, like in the olden days. We put them into an oily water settling tank, and then then we use an oily water separator that will make sure that it only removes water and not any oil-water emulsion, because if they settle long enough, the oil and the water will separate, and then you can just take a suction off the bottom, and then maybe you could pump that over the side. They really frown on that now, but back in the day, there used to be a lot of it. And then, to pump bilges, because there's water floating around down in the bilge all the time, you'd have to first prime the pump by way of using a venturi, actually using an air hose that would going through a venturi, and that generates a suction, and then you would be able to get it so that there's enough water inside that pipe, and then and then start the pump out, and then it'll start going onto the thing. And because I haven't talked about my wife at all, right? The first assistant engineer, he was sort of a buster, I wouldn't say first world, but he's asking me about my girlfriend. I'm like, yeah. He was like, do you ever imagine proposing to her? I'm like, yeah, sometimes when I'm down there and pumping bilges, just at the end of the day, she goes. And so from then on, it's, hey, there's bad names. It starts with F, right? F and cadet. Go propose to the bilge pump. Sorry, it just comes to mind every time I think of that priming that bilge pump. Like, and it took a while. You were sitting around waiting. All right, so that was an embarrassing story. Other problems for to do. I don't even know what time it is. I can't find my phone. There it is.
Like 11 minutes.
11 minutes? Ooh, what's we doing? 11 minutes. 8.
Oh, 8. Yeah, sorry.
That's all right. We didn't do a pump matching problem. And then once again, it's because of this project I didn't assign that last homework. All right, that last homework, I was like, we're just trying to cram this in here. But I do think it's an important thing to recognize the nature, important in not only that you should want to know about pumps, but in other types of situations, when you're trying to be a design engineer, as a mechanical engineer, you find this trend of two competing, of load and prime mover, think of it in those terms, right? When they have a relationship, and when you match them together, you find their equilibrium. And you could make the argument that you could figure out for a car that has a certain weight and certain tire sizes and all these things right here, you could say that this is its performance, or this is its relationship with speed, and then you could take an engine and match it with that, right? And just willy-nilly sticking any old damn engine into any old car chassis is really an ignorant thing that gets done all the time on the TV shows, but it's stupid, because you really should be an engineer and actually match the engine with the system, because you're being very wasteful in trying to do that. Yeah, that's why you have these low power cars that can blow the roof off of the big engine cars. Like, why does a Porsche kick the holy hell out of every one of these monster garage kind of things, right? Because the people who are putting engines into any old damn chassis don't know what the hell they're doing. It's like, more is better.
Get a Miata.
No, they need to buy. What's that?
Get a Miata.
No, it's not a get a Miata. It's be an engineer and match the load and the mover, right? But anyway, just my opinion. Onto the thing. Like, it's an American thing. Bigger's better. That's why we lost so many races. Okay, cool. Just go ahead. Shove as much power as you possibly can. Yeah, fine. But the whole idea, the whole concept, being an engineer, match a system, match the thing up. That's right there in the pump type of example, where we have the system curve and we have the pump curve, and they should match. And I don't remember how this problem goes, but I'll stay. Where we have a piping system curve of a 6-inch pipe diameter is superimposed onto a manufacturer's performance curve in the figure below. This is from fall '09 as well, so it's probably a stupid question, because I didn't know what I was doing. Find the following if the working fluid is water. The static head. All right, so what did I mean by that? I don't know. Find the static head. The operating point flow. I think I'm just supposed to pick this off the graph. This is not the problem. I'm not even looking on the correct page. I'm not even looking in the correct solutions. What happened to them? Although I should also say that I've never matched an engine with a chassis, so I don't know if I know what I'm talking about. The static head, the delta P plus the Z. Oh, the static head, I guess maybe, these are word definitions, because we're talking about this right here. This is the static head. You have the delta P plus the Z right there. And I guess if you did Bernoulli, it would be become a little bit, you had, damn you, I'm getting tired. I have to do another one of these in the afternoon. V squared over 2G. Yeah, that's a diminishing return sometimes, that coffee. But we have, remember that it's equals, damn it, P1 squared. I agree, maybe coffee is the solution. But these head losses are going to be zero. You think about if we're talking about the static, what we're meaning is like a zero flow rate, right? And so here was the hint that it was the delta P delta plus the delta Z. These are going to be zero, obviously. I mean, they might be zero because of the system. We don't know, but we do know when there's zero flow, they're definitely going to be zero. And we're going to have the delta Z right here. So we're also going to have no losses because there's no velocity coming through here. So we could really say that this delta P, right, at the P2 minus P1 over gamma plus Z2 minus Z1, right, is going to be equal to HP. So that's the static one right there. So that ends up being part A is saying that that's going to be 40 feet. The operating point gallons per minute and this right here. So that looks like it's 1600. Which makes it a silly question here. I could have put it over a pump, a pump problem that had multiple things in it, but I guess I did. And pressure. And so the pressure, and I decided, I put it in feet, right? So H is the operating point. I don't know, is that 65? Yeah, it looks like 65. I might even go approximately. The hydraulic power and power isn't on this right there. Efficiency is though. So you go H gamma, and then Q, I guess, or V dot right there. And we divide that by 550. Sorry about that. So 65, we said that this was 62.4 was given. The flow rate was 1600. Remember, we need to divide by 7.48 and 60 in order to get gallons per minute into cubic feet per second, and divide by 550. And we can just write down what we have. 26.3 horsepower. I asked for the pump shaft horsepower. And so we really kind of need the efficiency from this, and from that we can keep going up here. We can see, we can estimate that efficiency. I said that it was like 0.85, but it's kind of hard to see right in there. I guess maybe if you cross right in there, you get a 0.85. So the pump power is going to be the hydraulic power divided by the efficiency. So you take the 26.3 divided by the 0.85 and end up with 30.9 horsepower. And then this has the 12 feet per second limitation, and I'm trying to wonder where it says 12 feet per second limitation. The 12 feet has the 12 feet per second. 6-inch pipe, there you go. But it doesn't say, oh, you know what? I think that was something that I did mention in that class. There's a little bit, there's like a rule of thumb guidance when it comes to pipe sizing that I don't think I ever brought up in this class. I don't even remember it, but now I vaguely recall that there's like a guidance in one of the pump books that says don't go above like about 12 feet per second when it comes to selecting a pipe. There's a ton of rules of thumb when it comes to engineering things like that. pick them up as you go along, because if you don't use them for a while, you forget. So, we could find what the velocity from this. We take Q and divide it by A, but we have, and it might have saved us a little bit of time if we had calculated this out before, but 1600 divided by 7.48 divided by 60 divided by pi over 4, and this is 6-inch pipe, so it's 0.5 inch squared. And according to this, it's like 18.2 feet per second. So the answer is yes. It has exceeded 12 feet per second, so probably want to use bigger pipe. But then again, that pipe curve, the system curve, is based on that 6-inch pipe. So, we're gonna mess around, make an Excel spreadsheet, that's the answer. Make an Excel spreadsheet. And then you can do your little design thing and decide, oh, okay, yeah. We're able to stay within our guidance limits. All right, so, we're done, right? Hopefully it'd be helpful. Honestly, I don't know. I should have written an exam beforehand. But there's a lot of things I should have done. People were the project. You've got almost done. Almost done. Almost done.
Well,
Yeah.
So for that, like, edit that, like, do you mind if I make the parachute thicker?
I don't mind.
Okay.
I'm just hopeful that that you're gonna, you know, I want you to succeed. And,
Okay.
I don't.
Okay.
So I'm just a minor amount of concern that you're facing a struggle. I don't know if I can answer your question.
Paper down, just move it up.
Yeah.
Always get them all.
Alright, what is rated in my like project that like I had to do this for constraints because of software limitations, but
No, I hear you.
it's part of the